Familiar reaction that you can look at in the fall and to celebrate Halloween as well, investigating a particular way of decomposing hydrogen peroxide. And it's also known as elephant's toothpaste, but we're not quite doing it in a toothpaste tube here. Safety, goggles, lab coat, it's a demonstration, so students at least 2 meters away. And the chemicals involved, 30% hydrogen peroxide. You need to have your gloves, your lab coat and your goggles on throughout the experiment and the cleanup. And the cleanup can be done in the sink with good amounts of water. You can pause this to get the list of materials that you're going to need, and not going to read through all of those now. With the procedure though, you're going to have a carved pumpkin, and you're going to place aluminum foil inside on the floor of the pumpkin. Don't cover the eyes or the mouth or the nose. And then you're going to measure the amounts out very carefully, and remember, gloves, goggles, lab coat. And what I want you to do is to observe what's happening when the hydrogen peroxide is mixed with the dish soap in a 100 milliliter beaker. Then you're going to place that inside the pumpkin on top of the aluminum foil and wait until you're all ready to go, and then you will add the potassium iodide solution, and that's going to be your catalyst, and put the lid on the pumpkin then. And you're going to light a wooden splint, and you can put that into what egresses out of the facial orifices of your pumpkin, and note what happens, and be careful to leave matches and splints in water to make sure they're fully extinguished before disposing of them. So this is what you're doing. Some dish soap and 25 milliliters of 30% hydrogen peroxide. Be careful with that one. And then the cross section of the pumpkin here with the aluminum foil, and you've already added the dish soap and the peroxide, and when you are ready you're going to add the catalyst, the potassium iodide solution, and put the lid on the pumpkin, and then you're going to leave it for the reaction. It really doesn't take too long at all, and you're going to see a video clip which I've only put in the end part of the video.
Teacher who's your advisor and being in a lab for advisory.
Did you not film it?
No. You get to do fun stuff.
Will we be excused?
And to describe what's happening, so you're mixing a clear liquid with a second clear liquid and the soap. The soap has been added, so you do get the foaming reaction. And we've got hydrogen peroxide, which is being decomposed to water and oxygen, and it's that oxygen, the gas, that's going to bubble. You'll see as we've written the equation here, above the arrow we've put potassium iodide catalyst, and you're just going to pause at this point so you actually write the fully balanced equation. And again, the potassium iodide isn't appearing in the equation, just the reactants on the left, the products on the right, balanced, and we've got the states in there as well. So potassium iodide remains unchanged. You will see some browning as it forms some iodine and then goes back into potassium iodide, and the foam being formed with the soap. Hydrogen peroxide will decompose on its own without adding a catalyst, but it's pretty slow, often kept in a refrigerator to lower the temperature and reduce the decomposition rate, and it comes in an accordion bottle, which you may remember, and it's a brown bottle, so we're not allowing light in there as well. And adding a catalyst increases the rate of reaction by forming a temporary reaction intermediate, and you are lowering the activation energy, which makes the reaction take place more readily. And a reminder review of redox. Oxidation can be looked at as 4 different components. They don't have to all take place in the same reaction, and in fact many reactions don't involve oxygen or hydrogen. It's just a good guidance if it is in the equation and the reactant is changing. So adding oxygen to a chemical is oxidation. Removing hydrogen from a chemical is oxidation. Removing an electron, so if you're removing an electron from a metal, it becomes a positive ion. Increase in oxidation number, so you will go from maybe 0 for a metal to plus something for the charge on the ion that is formed by the loss, the removal of electrons. So they're all definitions of oxidation. And on the right here we've got reduction, which is the opposite of the oxidation definitions, but both occur in the reaction. You just don't get oxidation on its own, you get reduction as well, hence redox. And an example here, so magnesium is oxidized, you've added oxygen, an electron has been lost, in fact 2, going from Mg to Mg2 plus in the magnesium oxide product, and going from reactants to products, the oxidation number of an element is 0 and it's plus 2, which is the charge on the ion, but in oxidation states you always put the charge before the number. The oxygen is being reduced. It's gaining, in fact, 2 electrons to become O2 minus, and there's a decrease in oxidation number. The O2 is an element and its oxidation number is 0, and it's a negative ion in magnesium oxide, -2. So there's some review of redox as well. And very many thanks to WIS Team Science, Washington International School, Grade 9 Chemistry class, and Miss Hager.